Hello everyone and welcome to the session on Introduction to Artificial Intelligence and Transformers. I am Dhanashree Mishram and today we are going to understand about transformer architecture. The core engine behind models like ChatGPT, BERT and many of the state-of-the-art AI systems. You will learn how attention works, what makes transformer different from RNN and CNN, and how this model is applied across various domains like natural language processing, computer vision, and even in reinforcement learning. So let's begin with the problem with the sequence to sequence or a traditional models. So here in the RNN and the LSTM struggles with a long-term data. When there is a very long sequence of data, it will struggle. Okay, it will not going to give you the proper results. Same as CNNs will handle the spatial features well, but didn't scale with the sequences. So transformers can change the game here by introducing the attention mechanism, a way to let models focus on most relevant parts of the inputs. So here in the above image, we are having a input sequence or an input image, whatever. Okay, so here in the input sequence, we will convert whenever the new inputs will be coming, we can convert into token embeddings. Token embeddings are nothing but converting the each words or tokens into dense vector. Then there is positional embeddings, which will which will add all the informations about the positions of each token, since the transformer doesn't process sequentially or sequence-wise. Okay, so positional embedding here plays the important role. Okay, and then what we will do, we will sum up with adding the embeddings and the positions. Okay, like embeddings, all the numerical representation values which are in the form of dense vector, along with the positional tokens or positional embeddings, all will be summed in a one format. Then after that, we are having an encoder. In the encoder, this architecture is also called as encoder-decoder architecture. Within this encoder, we are having an attention and processing. Okay, so now the data will enter into the encoder block. So once each encoder has multi-head attentions. Okay, multi-head attention. What does multi-head attention means? It will have query, keys and value vectors. Okay, this query, keys and value vectors. They will perform a scale dot product between the query and the key vectors to measure the attention scores. Okay, to measure the attention scores. These scores go to a softmax functions. These scores will then go to a softmax activation functions. Okay, once they will go to a softmax activation functions, finally we can form a weighted sum. We can form a weighted sum by multiplying the weights multiplied by the value vectors, or we can multiply first with the weighted sum and the weighted sum will be multiplied with the value vectors. Okay, so the weighted sum of the value vectors gives the focused representations. Okay, and multiply each attention heads in a parallel to capture the diverse conceptual clues and information from each domains. All heads are concatenated here. All the heads means all the projections. All the projections are then concatenated, like linear projections followed by the residual connections. Then layer normalizations. These all together, like residual layers and the layer normalizations, both will combine together and then it will be processed towards the feed forward network. Okay, like we will concatenate all the heads, then we will form the linear projections. Linear projections then form a residual connections and layer normalizations. After having a residual layer and layer normalizations, we can have a feed forward network. The feed forward network takes all the inputs, all the heads, and then it will decode. So what will happen here in the encoder output will be generated. Okay, encoder output will be generated. So this track repeats multiple times. This will repeat multiple times. So there will be not only one encoder, there will be multiple encoders. Okay, so this track repeats multiple times depending upon the model size. The final results is the encoder output. Okay, so after that we are having whatever the encoder output we have got, then what will happen? The decoder, it will go to a decoder state. What is there in the decoder? So decoder will also uses the attention mechanism, but here there is a twist. Here there is a twist. There are two attention types. First is a mask multi-head attentions, and second is an encoder-decoder attentions. So what is first? The mask attention mechanism means it will ensure the model doesn't peek into the future tokens while generating the sequences. Okay, so we will do a masking. Then there is a encoder-decoder attentions. Within this encoder-decoder attentions, what will happen? It will help the decoder attends the relevant encoder output. Okay, based upon what? Based upon the mask multi-head attention. Along with the mask multi-head attentions, we will align whatever the encoder output is with respect to the decoder outputs. Okay, based upon that, it will use again the residual connections and the layer normalizations, and again a feed forward network which will take all the inputs from the layer normalizations and residual layers and make it into a decoder output. Okay, so this is how our output will be generated. Now, once this decoder output is generated, what will happen? We are using a final decoder output, which is a linear layer and the softmax function. Okay, linear layer and a softmax activation functions we are taking. Why we are taking this? To generate the probabilities over the vocabulary or the output space. So this results is an output sequence, such as it can be in a form of machine translation or translated text like how are you, and the decoder output will be I am fine. Likewise, it can be useful for predicted labels or a generated text format. Okay, some prompt you are giving and based upon that some text is getting generated. Okay, so now what are the different applications and multiple domains where we can use this? So there are these all applications are there where we can use this attention layers or a transformer architecture. Okay, so here we can use it in natural language processing. Where we can use in natural language processing means we can use it in translation, summarizations, question answering. If we want to machine translation, if we want to do like Korean to English or Spanish to English, likewise. So we can do it by using a architectures there are present, that is BERT architecture, which is bidirectional encoder representation of a transformer, and GPT. And then the one more application to this is computer vision. We can also do like image classification. We can use it in vision transformer, or we can use it in object detections. We can even use in a speech recognition like synthesis and transcriptions. Okay. Then reinforcement learning. Generally, this reinforcement learning is used for gaming. Okay, when there is some agents or environment is present, within that environment, agent is playing the game. So for all these purposes, we can use this reinforcement learning, and reinforcement learning wherein we can use it in attention mechanisms. Okay, we can use attention mechanisms in reinforcement learning as well. Then there is a domain-specific applications. A domain-specific application in the sense we can use it in specific cases like healthcare, finance, law. Okay, all these cases we can use it. Okay, so here what is the main thing is we are having a summary of all this thing. Okay, so here first what we did, we have a transformer architecture which replaces the recurrences with the attention mechanism. Okay, what was the recurrences? Like a sequence to sequence model we're having in the RNN, LSTM and GRU. So it has been replaced with an attention mechanism. they are parallelized, okay, and also having a context aware. So how it will form a context means it will take all the inputs and then based upon the alignment score, we will form a context vector. Okay, based upon that, we will form the context vector. So the thing which are very important, only that we will take, and the things which are not that relevant, we will skip that. Okay. Earlier in LSTM and GRU, we were having a gated approaches for this. Okay. So again, when there will be a very long sequence of data, they will not work. Okay. So attention scores lets the model focuses better than anything before. Okay. So attention scores, how this attention scores or alignment scores will be formed based upon the inputs and based upon all the heads. All the heads we will take whatever the alignment score is or whatever the attention scores is. The scores which are getting more, only that we will take into a neural network. Only that we will take. Okay. So today there are at the heart of almost every cutting edge AI models, we are having this transformer architecture. So now we have understood here about, first we have started with this input sequences. This input sequence will be there. This input sequence will be first converted into token embedding and positional encoding. Okay, and then we will be together added with an embeddings and the positions with respect to the embeddings. Okay, then according to that, we were having a multi-head attentions. Multi-head attentions for this particular inputs, whatever the inputs we are getting, how many projections we can have based upon this. So we'll take all the projections based upon that and we will form a multi-head. Okay. Now, one by one, each head we will take or each projection we will take and we will form a query vectors and keys. Okay. So here what is there? We will multiply. We will form a since this query and the keys cannot multiply because they key having different dimensions and the queries will have a different dimension. So what we will do, we will make a transpose of this. We'll make a Q into T transpose. T transpose, why we are doing? Because matrix multiplication is not possible here. The internal values between query vectors and the key vectors should be same. Okay, so we will do the matrix multiplication and then we will form a scale dot product here. Once we will form the scale dot product, we will form a softmax activation functions. After getting a softmax activation functions for this particular function, we will do a weighted sum. Weighted sum of all the inputs and the value vectors, multiplying with the value vectors. After getting this, we will concatenate all the heads. For first head, for the second head, we are having multiple head, right? For all the heads, we will do the same thing. And then we will concatenate all the projections, all the heads. Okay, all the projections or all the heads into a linear projections in a one layer, in a linear projections we will concatenate. And then we will add all these two layers together. Okay, we'll normalize that layer and then we will add that layer. Okay, and this feed forward network is nothing but it is used to carry forward this layer to the another output. Okay, so it will take the inputs from the residual layer and the layer normalizations and it will carry forward it to the encoder output. So this will continuously go as and how the new inputs will be coming, all the multi-head we will take, again all the same things we will do. Continuously we'll do the same thing. Okay, after that in the encoder now here in the decoder, what will happen? We will have the encoder output. So the encoder output is taken again and here we are also taking the multi-head attention, wherein multi-head attention here we are taking with the masking. Okay, here we can do a static masking also, we can do a dynamic masking also. So based upon this, we will take this both the encoder decoder attention and multi-head attentions, which will be mask multi-head attentions. And again, we will feed it into the residual and layer normalizations. Again, we will feed it into the feed forward network and again it will form a decoder output. Now this decoder output can be useful for, like we will use with the softmax activation function and we will form a linear output for this. And this output sequences can be useful for all these operations. I hope it is clear. For all these purposes like natural language, mostly we are using this for natural language processing, and multiple like domain specific knowledges like healthcare, finance sectors, genome sequencing, all these things we are using this architecture. Okay. So this is very, very, very important architectures, and nowadays we are using it for everywhere, like generative AI, other where we are using this transformer architectures. Okay, so now we will jump into a practical part. Here what we are doing is we are importing NumPy. We are splitting all the heads. So we are finding, we are doing what? We are having a user-defined function for splitting the heads. Okay, so while splitting the heads into multiple heads, okay, we are having what? We are having match size, we are having sequences, and we are having the model. Okay, so here we are taking multiple heads and we are splitting all the heads by one by one by one like this. And then here what we are doing in the multi-head outputs. Okay, in the multi-head outputs, we will combine all the heads. All the heads will be combined together. Okay, suppose for example, if you are having one head here, so like you are adding one more head. So here will be the two heads will be there with 4 features like this. Okay. So after that, we are having a combined head. In a combined head, after each head computes the attention separately, we will combine them back and reverse the splits again. We will reverse the split again. Okay. Likewise, after this, we are having a function for scale dot product. Scale dot product will do what? As I have told you in the architecture, it will do a matrix multiplication between queries and the keys. But queries and key matrix multiplication is not possible. So we will do the K of transpose. Q into K of transpose. Okay. So we are taking a transpose of K and then we are multiplying with the attention scores. Okay. So queries and the keys are then multiplied. After that, how important are all the other words for me? Okay, we'll decide how important all the other words are for me. Likewise, we can have scores, how similar each word is to the other. Likewise, we can have a scale the scores that will prevent the exploding values. Okay, so we'll remove that scores which are exploding the values. Okay, then we will combine the results from all the heads. All the heads. So we have splitted all the heads, then we will combine all the heads, and then we will have learn the different relationship in the sentences. Okay. So this is what the main thing, the scale dot product and the output of the scale dot product will. Okay. After that, in the attention head, again, we will do an attention head for all the head, queries head, key heads and value heads. For all this head, we will do and combine all the relationships between them. Okay. So likewise, we will do, and then we are forming a simple feed forward network. What is this feed forward network is? This is a basic neural network after attention, which will work like it will add all the layers from the multi-head and then carry forward to the layer residual layers and the layer normalizations. That's it. Okay. This is how you are having all the layers and we will take it to the last layer. Okay. After that, we are having here we are having one dummy data. Dummy data we are creating. Okay. Just a dummy data creating. Okay. So we are taking a batch size of 1. We are using a 4 words. 4 words. The sequence of sequence underscore length means 4. That means only 4 words we are taking. Each with the 8 features. Okay. 8 features we are taking for the 4 words. Okay. And then we will pass them into the transformer encoders. Now it will do what? It will get back the updated representations. Updated representations we will get from here. So you can see here after running this, we are having all the representations for this inputs. Okay, what is this one? 1 means nothing but a batch size. 4 is your length. What is the length? 4 is your words. Okay, or a sequence length that we have given. And 8 is nothing but an each word has 8 features. So features of this. So this is how the architecture will be forming. Okay. So this is all for today, guys. Today we have understood about the basic architecture and the basic model we have seen. Okay, how the transformer architecture internally works, that we have seen. I hope it is understood. We will meet with the next topic on the next Monday. Okay, thank you for joining.